There we go. Can y'all hear me? Okay? Volume okay? Good. I got myself a new fancy microphone now, so I'm trying to make it so that it's not too close or too far. So if the volume needs to be cranked up, let me know because this is only about halfway or so. Let's see. What was I going to say? I lost it. Probably nothing important then. I'll just say hi. Oh, I know what it was. Homework one was what I was going to start with. So I peeked at the data set that's online just a few minutes ago and saw that you guys have a almost perfect bimodal distribution. Some of you have finished it already, and some of you haven't started. So I was hoping to call on some of the folks who finished it to get their input as to how terrible it was or wasn't. So Jen, I warned you that I was going to call on you. Do you want to tell the other folks what your experience was like in finishing it?
Yeah, the most difficult part is figuring out how to turn on everything, and making sure that all the file paths are right, like Dr. Hoffman has been saying. Make sure that you read each question and actually do what it's asking you, because Stata will do what you tell it to, and it's not always the right thing. And then there'll be a red box for 30 minutes, and you're very confused.
Those are good points.
But it's not too bad.
Good. Do any folks who are working on it still have questions?
So I plan on coming to office hours to ask questions, but basically I finished everything except the last part.
Okay.
And I feel like that's the part where it's like, okay, well, if I could get 100 on this homework, then I'm not going to submit it yet because I want to make sure that I fully understand these concepts because I know I only get one chance at these as opposed to the other. But I felt like the other parts are pretty straightforward, as in plugging in and trying to see if it works. And then you get the green light if it all works out, and then changing in at the bottom of each section. I thought it was helpful to reinforce some of the things that we've learned as well with the Madlib pieces.
Good. Yeah, so the as he's saying, the drop down menu questions, the results questions, or the interpretations, those you will only see if you get a correct answer after the deadline for the homework passes. And I am happy to answer questions about those. My policy is that I can't directly say whether you're right or wrong, but what you can do is tell me the logic that you're following to get to that answer, and I can tell you whether the logic is solid. So there's a fine line between the two. But I'm happy to have you sort of talk through your answer if that will make you feel more confident that you have the right answer. By the way, if you ever get any of you gets industrious and finishes it early, and then we talk about something in class and you realize that you want to go back and change your answer, just shoot me an email and I'm able to reset your entry from my end so that you can change your answer. So long as it's before the due date, I'm happy to do that. That's fine. Otherwise, just don't forget to actually submit it once you decide that you are as finished as you're going to be. After you click submit, there's an extra step in which you re-enter your 8-digit Iowa ID and then you hit submit again. And I have that extra step to prevent anyone from accidentally submitting for good before they are ready. So just don't forget that last step. If you do forget it and you realize after the deadline has passed that you've forgotten it, again, shoot me an email and I can fix it on my end. So I'm not. If it's an honest mistake, that's fine. I can live with that. Any other homework questions that I can help you with right now? No. Okay, and then I have the schedule pulled here. Can you all see the website with me? We're good on the scare. All right, good. I was going to point out that this week we're likely to be finishing lecture 2 and example 2, which means that I will be putting up homework 2 that goes with them, probably by the end of the week or the beginning of next week, which will be due in 2 weeks, 2 weeks after homework 1. So basically you'll have something due once a week from this point out, either a homework or a formative assessment. And just to remind you that a week from today, we have an off day. We haven't, like, the university decided since they're not giving a spring break that they're just going to give us a random Tuesday and a random Wednesday off, and that happens next week. So next Tuesday we'll not have class or office hours, but if you do have questions about anything, you're welcome to shoot me an email, and I'm usually pretty quick about those as well. So, all right. So then here's a lovely picture of the beach while we do some review. Tell me what you remember from last time. As usual, I'll take letters, words, gestures, phrases.
Pearson's
Yeah.
Pearson's
say
are.
Jen.
Let me speak, Jerome.
Okay, Jen first and then Jerome.
Pearson's R doesn't understand nonlinear relationships.
Yes, it does not index them. So if you have a U-shaped relationship or any other thing that's not a line, Pearson's does not pick that up. Did I tell you how we are going to pick that up?
With a Spearman correlation.
That is another type of correlation, but it's still a linear correlation. It's just on a different set of data. So to index nonlinear relationships, we need a model. We need to be able to predict a quantitative outcome from quantitative predictors and to specify the functional form of that prediction. So that is coming in lecture 4, actually. Jerome, you were going to say?
I was just going to say that Pearson's is for linear, and in order to smush in some of the sides that are not in that linear progress or linear one, then we do Spearman's to get those to come in closer so they are more in the line.
Yeah, smush in the sides is a good way to visualize that. What's actually happening under the hood when you ask for a Spearman correlation? Do you guys remember? Or ladies, I should say. Do you folks remember?
I just remember that it moves our X's in further. So that's why I said smushing, but I don't remember, I guess, technical terms for it.
You are remembering, let me pull up the picture. I think you're remembering this picture maybe. This is slide 24 of lecture 2. So Spearman actually smushes in the X's and the Y's because it changes the data that the correlation is being computed with. So Pearson correlation indexes a linear relationship between two quantitative variables directly as they are. And in describing the size of that relationship, it standardizes the variables. So we have covariance as the intermediate step that includes the standard deviations of each of the variables as part of that value, which makes covariance not as interpretable. If you divide the covariance by the standard deviations of each of the two variables, then you're into correlation land. So you can think of a correlation as between two z-scored versions of a variable. But it doesn't do anything about extreme values or non-normality or any of that stuff. It just changes the metric of the two variables. So the smushing or the squishing happens in Spearman's correlation because Spearman's correlation operates on rank orders. So it translates the values of a quantitative variable into a rank order system where the lowest value is a 1 and the next lowest is a 2 and the next lowest is a 3. And it does stuff if there's ties, but I don't think we need to focus on that. And it's that rank ordering that causes the smushing. Because then it's like, if you have a value that's like 1, 2, 3, 4, 5, 6, 7, 8, and then the next one is 12, under a rank order, it becomes 9 because it's the next one after 8. And so that effectively reels in extreme values. And so you can end up with a Spearman's correlation as a way to address potential influencers, not the kind on social media, but the kind where it's like the randos, as I said, like this picture right here on slide 23, the guy over up here in the top right hand corner, you can think of that person as an influencer for the line. It's pulling the line away from the rest of the data in a disproportionate way. So if you're concerned about those sorts of observations, Spearman's correlation is one way to mitigate their influence, I would say, to reduce their influence. And Spearman can also be used for ordinal data, which is functionally a rank order in most ways that it's coded anyway. So, good. Anything else you remember?
Can I ask a question about that, Lisa?
Please.
So could you, I'm just trying to make sure I understand, how would you utilize that in a way that's not you're not trying to skew any data? Is it just visually you're trying to make it look more I guess clean? Or could you give me an example of when you might utilize that to take that sort of outlier without making it without trying to make it look like something it isn't?
Yeah, I think I can. The example that we used, I have a picture that I'm thinking of that might help explain this. So this is example 2 that I'm scrolling through that we did last time. Yeah, so for instance, this picture that I'm looking at right here is on the x-axis is the original income variable, and on the y-axis is a log transformed version of it. And so the purpose of a log transform would be to sort of reel in those values. You can think of Spearman as doing the same kind of thing. The question would be, if you're looking at, say, the relationship between income and education, if you know that there are a few cases that make a lot more money than the other cases, to what extent are they driving the relationship between education and income? If you're concerned about that, then either estimating a Spearman correlation or estimating a Pearson correlation on a log transform version of the data, they're both trying to do the same thing, to reduce the extent to which extreme cases can be driving that linear relationship. So thanks for the question. All right, other questions or things that you want to clarify or hear again? And I can hear my little laptop's motor spinning and spinning and spinning, which means that I need to shut something down. Let me close my Dropbox, which is usually the memory hog problem here. Okay. Otherwise, all right, then if y'all don't have any other questions on there, we can head back into where we were last time. So I'm picking up in lecture 2 with slide 24 is what we were looking at here. I wanted to introduce you to another kind of correlation. This one, by the way, is just an FYI for your life. This isn't one that I'm going to expect you to do in homework 2. So the terminology here is intraclass correlation. And this matters in the context of using correlations as indicators of reliability. So have any of you worked with qualitative data where you need to do like an inter-rater reliability check? Yes, Fayaz, have you? Do you want to give us an example of when you would do something like that?
So in my qualitative study, what we would do is we would do so when I'm analyzing transcripts, there would be 2 reviewers analyzing the transcripts, so that I'm not giving a biased analysis of the opinions expressed by our respondents.
And how would you assess whether or not you and the other person reviewing it are sufficiently consistent with each other?
I guess if the codes are same, when we are coding the transcript, so it's like maybe an hour of interview that's broken down into several codes. And so if the codes are compatible with one another, like if our end codes, and then like we would distill this to maybe like 20 sentences that are like that we could categorize into codes. So if there is match between those codes, then we would say that there is congruence, or like we concur with each other.
And so do you ever do an analysis that would actually test the extent of congruence?
No. My qualitative, like I didn't do any in-depth qualitative analysis. This was like for a class project.
That's fair enough. And so when you say codes, do you mean some kind of like number that represents a type of attribute? So it's a 1 if they did this, it's a 2 if they did that kind of thing?
No, it's qualitative, right? So it has to be words.
Okay.
Yeah.
So the context I'm thinking of would be where, let's say you're watching a dialogue between, say, a mother and a child, and you're coding the dialogue for certain attributes. How warm was the mother? How patient was the mother? How attentive was the child? Those sorts of things.
But
And
would that still be qualitative? If I
that's as qualitative as I get. Let's put it that way. So to me, because there's sort of a subjective judgment, like the thing that you're watching or rating is an action. You know, it's a video recording in most cases, or an audio transcript or something. And so a lot of times people will try to create numerical quantities that represent aspects of that interaction. But it's the same whether you're deciding on a number or a value judgment, it's the same idea though. Like, how do you know that your opinion of what this transcript says is the right one? Like, would someone else come to the same conclusions as you? So that's a big deal whenever you're trying to have an outsider provide the data. So like you're rating something. In that context, a lot of people would think, well, I have the ratings from, say, reviewer 1 and I have the ratings from reviewer 2. And because they're both supposed to be focusing on the same targets, these ratings should be correlated. So why don't I just look at Pearson's correlation to see the correlation between these ratings, or Spearman's correlation? And that's actually not a great idea when it's in this context of reliability, because mean differences matter. So if you were looking at absolute agreement, so reviewer A says, I think this kid is a 3, and reviewer B says, no, that kid's a 4, right? Reviewer B might be systematically higher or lower. They might be more conservative or more lenient across the board, in which case their scores would all be higher sort of to the same extent. Pearson's correlation would think that there's a perfect agreement there, even though they don't actually agree. So to be able to index actual agreement, like, no, I thought this was a 3 and you thought this was a 4, so that doesn't match, you need something called an intraclass correlation instead. And the key difference is right here. You can see my pink mouse here, where covariance used to be. Rather than deviating each variable from that variable's mean in particular, it gets deviated from a common mean across the two. That's the distinction. So if you have two y's, meaning that there are two variables that are supposed to be referring to the same thing, you would compute a common mean for them and then deviate the scores from that common mean. And so intraclass correlation is able to pick up absolute differences as well as relative differences. And it works out then to a ratio of how much of the variability in these two variables is due to differences between the targets that you're rating, which is supposed to be the case, versus differences between the raters, so sort of systematic, one person is more lenient or more conservative, versus some kind of error that they're just disagreeing and we don't know why that is. And so if you have taken any classes in generalizability theory, you'll recognize this sort of idea. There's different ways of using intraclass correlations to talk about absolute agreement versus relative agreement. One nice thing about this particular approach, though, is that it can generalize to more than two raters. So if you had a team, for instance, a team of coders who are all rating the same thing, you could use this type of intraclass correlation to get an estimate of their reliability regardless of how many you had, and if you do it with the right type of estimation, regardless of whether everybody rates everything. So I just wanted to show you this. Put a pin in your memory. If you ever need to assess reliability, just think intraclass correlation is what Lisa said and ask the Google about that. And I'd be happy to send you more examples, but that's the word choice that you'd want to use. This is for quantitative information. There's other ways of assessing reliability for categorical information when you have to like make a categorical distinction as opposed to a quantitative one, and that's coming later in the show. So, question?
So when we are using, like, let's say that we are using interclass correlation for a specific study, do we use it alongside inter-rater reliability or instead of inter-rater reliability?
I would say you would use it for inter-rater reliability. Like that, the number that this provides you is your index of reliability. And based on the context, you can decide whether you want absolute agreement or relative agreement. Okay, other questions? So again, all right, put a pin in that. So this is just a picture that's trying to illustrate the differences of when you would see a different number for a correlation that is just a Pearson correlation versus an intraclass correlation. And it boils down to whether or not there's systematic differences in the mean and or the variance across the variables that you're relating. If there is, then the intraclass correlation is going to be lower because you're going to have less absolute agreement. So This concept also shows up in multi-level modeling, which is another course that I teach after this one, and I'll teach the clustered version this fall, to talk about proportion of variability due to different sources. And so this is intraclass correlation is a common thing that you'll see in a lot of different contexts. Binary variables. Cough, cough, homework question. Cough, cough. For homework 2. You can use Pearson's correlation to describe the association between two binary variables. There's nothing technically wrong with that. However, it is not going to be the best way of doing it to the extent that the binary variables do not have means of 0.5. So recall that in binary variables, the variance of a binary variable is not a separate thing the way that it is for quantitative variables. For binary variables, the variance is calculated as the proportion of people who have a 1 times the proportion of people who have a 0. So only when a variable is split 50-50 would you have the maximum variability. And as a variable's mean moves away from 0.5 on either side, it will necessarily have less and less variance. And eventually, if everybody has a 0 or everybody has a 1, then you would have no variance whatsoever. So variance is constrained by the mean. So if you have two binary variables whose variance is each constrained by their means, that means their covariance is going to be constrained by their means as well. And so this table here is showing you the results of what happens. The maximum covariance that two binary variables can have, and thus their maximum correlation, is a function of their means. So for instance, if I have an x variable where 10% of the cases have a 1 and 90% of the cases have a 0, and I want to see if that is related to a y variable where 20% of the cases have a 1 and 80% have a 0, even if those two variables are perfectly related, the maximum Pearson correlation that they can show is 0.67. It's not 1. So you can think of this as an instance of range restriction, where the maximum relationship that is possible is not the maximum that it should be. Because correlations should go all the way from -1 to 1. In binary variables, that's not going to happen unless they both have a mean of 0.5. So keeping that in mind, people have developed other ways of getting correlation type estimates from binary variables as well as from ordinal variables. And so I just wanted to, I think that's the next slide anyway. Yeah, so I wanted to just put another pin in your minds that there are all these other kinds of correlations that you may come across in your world. This is not something that we're going to get to in this class, but they do show up in some of the advanced classes, and so I just wanted you to have heard these words before. So in binary variables, if you're interested in showing a correlation between two binary variables, a better way to do that than Pearson's is what's known as a tetrachoric correlation. Well, that's a mouthful. It is not the same thing as a Pearson or a Spearman correlation. So I see that one in the latent trait measurement course that I teach, the structural equation modeling course, as well as polychoric is the other one. That is a correlation between two ordinal variables that is not the same thing as Pearson or Spearman. The math underneath them is kind of nasty, but the concept is that they are correlations between the underlying continuous variables that gave rise to these categorical or binary versions. So it's a little like out there, but just know that if you're working with binary or ordinal data, then these are better ways of getting a relationship between them that do not have the same problems of range restriction that a Pearson correlation does. So just, and again, putting a pin in here that these things will show up elsewhere in statistics when you're dealing with categorical stuff. All right, so next topic is a change of shift. Questions, comments? All right, so the big picture of what we're talking about, bivariate association, relationships between two variables. We've talked about how to do that for for a pair of a quantitative variable with another quantitative variable, or quantitative with binary, Spearman can be used for ordinal, but more common if you have categorical with categorical as the type of variables that you want to see that they're related, especially for nominal, is another way of looking at it, which is known as chi-square analysis, which is based on the idea of a contingency table. So I first came across this, by the way, in like introductory biology in college, when they were talking about Mendelian genetics and dominant and recessive genes and stuff. That was where I first came across this. So this shows up in a lot of different contexts. But the idea is that if you have a pair of categorical variables, so whether they're binary, nominal, or ordinal does not matter for this distinction, you can put together what's known as a contingency table of how frequently each possible combination of values is observed, and then you can find out whether or not there is an association between those cells that's different than what would be expected just based on the frequencies overall of each of the variables. So to do this, I'm pulling up an example here from the textbook that goes with the class, although I don't use the textbook for much. This is archival data that was featured in the textbook that was looking at the propensity to receive a death sentence in a criminal proceedings corresponding to the race of a defendant, in which they've simply categorized it as white versus non-white. And so in this table right here, the 2x2 combination of yes, no versus white versus non-white, these are known as cells. So that's a particular combination of a value on one variable crossed with a value on the other. And the totals out here, either the totals for a row or the totals for the column, are known as the margins. So for instance, there were 284 non-white people included in this analysis. Of those 284, 33 received the death penalty and 251 didn't. Likewise, if I go down here, there were 66 people in the analysis who received a death sentence. Of those, 33 were non-white and 33 were white. And so this table by itself is just a descriptive statistic. It's giving you the frequencies of what each of these combinations has been observed. But what we can do is use the information in the table to figure out whether or not these two variables are associated. And so this we will do in SAS proc-freq. So proc-freq is the same way that we get frequencies and percentages for one variable at a time. We can use it to get frequencies and percentages for a combination of multiple variables. Stata, it's tabulate to get the table, and then tab 2 and CS to get the chi-square statistics. But the idea of a chi-square here is to generate how many people would be expected for each of these combinations, and then compare it to how many people were actually there. So expected is computed as the number of people in a row times the number of people in a column divided by the total number of people. So for instance, based on just the number of non-white people in our analysis, and based on the number of people who received the death sentence, how many non-white people would have received the death sentence if these variables had nothing to do with each other? So that works out to be 284, which is the margin for the row, 66, which is the margin for the column, divided by the total for the entire table, which is 825. So that's 22. So the expected count for the top left cell of this design is 22. So the numbers inside the parentheses are expected counts. That's why they're decimals, because you can't have a 2/3 of a person, right? You can't have 0.28 people and 0.72 people. They're expectations. So the gist of the analysis then is taking each cell and comparing, okay, how many people did you actually see in this combination versus how many people would you have expected if these two variables were unrelated? So there are more non-white people than expected who received the death sentence There are fewer white people than expected who received the death sentence. There are fewer non-white people who did not get a death sentence, and there are more white people who did not get a death sentence. The question then is whether or not there are significantly different from expected versus observed. Okay, with me so far? Ish. Okay. So how do we know if there is a big enough difference between what we found and what we would have found if the null hypothesis of no association were true? We add it up. So the chi-square is a test statistic that comes straight out of the table. So this analysis works kind of backwards relative to correlation. So when we were looking at correlations between quantitative variables, step 1 was to get the correlation estimate, step 2 was to get the t-test for it, and then step 3 was to get the p-value. This goes backwards. Step 1 is to get the test statistic, step 2 is to get the p-value, and then you can work backwards from there to figure out what an effect size would have been. So it's a different approach, it's just the same 3 ingredients: size of relationship, test statistic for whether that relationship is different than the null hypothesis, and then the p-value that goes with that test statistic. So this is a new test statistic. This X looking thing right here, that's called chi-square. It's actually chi is the X part and then it's squared. So the squared should point you towards the idea of what this value could possibly be. Squared numbers can only be positive. So this is a test statistic where the smallest you can have is 0 and it goes up from there. So the way that it is computed then is to take each of these cells and take the observed, so for instance the 33, minus the expected, the 22.72, square it, that way the deviations don't cancel each other out, so same idea as variance, and then divide by what should have happened under the null hypothesis, the E for expected. And so then if you do that for all 4 of the cells, the math works out to 7.71. So that's my test statistic that tells me whether or not there is an association between these 2 variables, given what happened in the cells. And in this case, what we need to know is how many degrees of freedom were possible for the table. So this is a different degrees of freedom than what we had for T, which was denominator. So this is your first instance of seeing what is called numerator degrees of freedom. Comment, I can't believe I used to calculate chi-square by hand in prior stats classes. Well, to be fair, I sort of did it here for demonstration purposes, right? But yeah, in life, no, we don't calculate shit by hand. That's not how it's done. The computer is better and faster at it than you. But conceptually, though, I think it might be helpful to see just how the numbers shape up. The concept of the chi-square is comparing sort of what should have happened if these things were independent versus what actually happened and seeing if those numbers are off from each other. That's chi-square. The problem is that chi-square, because it's in squared units, doesn't tell you directly which way off is. So these numbers could have been different than expected because white defendants were more likely to get the death penalty than expected, or because white defendants were less likely than expected. Knowing that the chi-square is 7 doesn't tell us which of those possibilities it is, because chi-square is squared. So unlike T, that has the same sign as the correlation, this one does not. So we have to do a little more digging to be able to interpret this. But in terms of degrees of freedom, there is, let me back up for just a second in this here and find another slide that has degrees of freedom, because I think it's useful to see it side by side. This one right here. This is slide 15 I'm returning back to for just a moment, because I wanted this table right here. So how do you know if you have a relationship between variables worth talking about? The way that you would judge that relationship, a test statistic that maps that relationship onto where you would be with the null hypothesis, uses 2 pieces of information. One is sample size. So sample size is denominator degrees of freedom. So T uses sample size, and its cousin that you haven't met yet is F, which also uses sample size. But the other piece of it is how many pieces of information do you have to know to be able to talk about that association? If you're testing, say, one correlation, then you only need to know one thing. The number of things that you have to know is referred to as numerator degrees of freedom. And so Z is if you're testing one thing and you don't care how many people you have because you have enough people that it doesn't matter. And chi-square is Z squared for testing more than one thing. So we started off with Z, realized that Z doesn't work if you have small samples, and so we moved to T. Now we're back over here to chi-square, which is not caring about how many people there are and testing more than one thing. So we have to know how many things we're testing inside the chi-square to be able to figure out whether or not our chi-square is significant, different than expected. Going back to where we were. So this is slide 30 again, picking up where I left off. So in these sorts of contingency table analyses, the degrees of freedom for the numerator is the number of rows minus 1 times the number of columns minus 1, so 1. Basically, the idea here is that if you know, sorry, hide this thing, there we go. If you know how many people are in one of these 4 cells, that's all you need to know. You can figure out the rest. So in the data set, I know there's 284 non-white people, and I know that there's 551 white people. If you tell me any one of these cells, for instance, you tell me this cell right here is 33, okay, well, I know that if there's 33 people here, then it has to be 284 minus 33 over here, that's 251. And if I know there's 251 here and the total is 759, then I know that there has to be 508 left. So you only have to know one thing to figure out the whole system. You would have to know more than one thing if there's more than 2 rows or more than 2 columns. So it's one thing to figure out the system of relationships. Degrees of freedom for the numerator equals 1. And so that is your standard as to what you would compare this chi-square test statistic to. So on its own, 7.7, you don't know what to do with that. It's like, is that good? Is that a lot? Like, what should it be? It depends on the number of degrees of freedom that go into it, which is based on the number of things you're adding together. So a chi-square distribution has a different shape depending on the number of degrees of freedom for the numerator. So we are this yellow line right here. That's what it looks like if there's only 1 degree of freedom. So the same idea of where does unexpected start applies here, but it only applies in one direction because chi-square is only positive values. So where do we want unexpected to start? A little bit of review here. What am I asking? If I say, where does unexpected start, how would I translate that concept into language? What controls where unexpected starts in terms of talking about our results?
Is
That
this
be
where
the
you're looking?
alpha? Oh, sorry.
I was going to say that too. So.
It is the alpha. Good on you. Yes, alpha. Alpha is an area. It is the area under the curve where something would happen less than some % of the time. And our conventional alpha, this is a finger question you can answer. What's our conventional choice for alpha in the social sciences? Yeah, 5. Yep. And that means that we have a conventional level of confidence for where expected is of 95. So if I take that and apply it to this picture, before we had a test statistic that had 2 sides, right? Both Z and T had 2 sides. Do you want to see a picture again? Or is me doing this sufficient? This is good? Okay, yeah. So Z and T look like a mountain, right? And because we don't do bullshit voodoo in this class, we don't do one-tailed tests, we only do two-tailed. That means that our total 5% for unexpected, 2.5 of it is on one side and 2.5 of it is on the other, because we accept that a result could be positive or negative relative to what we put in the center as the null hypothesis. Well, this thing can't ever be negative. Chi-square, by definition, if you square a number, you can't have a negative number. So the area is all on the right here. So the cut point for where unexpected starts for 1 degree of freedom is right here. I have a label. It is 3.84. That is the chi-square value after which 5% of the area is expected to happen. So that translates to any chi-square for a 2 by 2 table, meaning 1 degree of freedom, is a significant chi-square. The association is significantly bigger than what would be expected if it's past 3.84. So our value was 7 something, which is out here. So because we are out past where unexpected starts, sorry, this way for you guys, we're out this way, this would be a significant chi-square, but we don't yet know what the pattern is until we drill down into the table. We just know that there is some kind of relationship between the race of the defendant and the eventual decision. And we can get an exact p-value out of this distribution. So we would observe a chi-square as extreme as what we found if there really was no relationship, less than 1% of the time. So 0.00549. So very small. The curves change shape, though, depending on what your degrees of freedom are. So if you had degrees of freedom 2, that's the green line. That one, the critical value, which is not on here but is in my head, is 5.99. So right here would be where unexpected starts. For the teal line, where degrees of freedom 3, that cutoff value is 7.82, which is out here. Because yes, once upon a time, I had to do shit by hand too. So I have these things in my head still, back when I had to refer to some table of where chi-square values were. So for 1, it's 3.84. For 2, it's 5.99. For 3, it's 7.82. And for 4, it's 9.49. Those are all the alpha 0.05 cutoffs that live in my head. After that, I stopped memorizing. But you're not going to memorize any of this because your program is going to tell you the p-value. So I'd say it's impressive, but not really. It's like one of those like nerd things that I should be not necessarily proud of, but it's up there. So point being, big picture here, chi-square is a test statistic used to tell us in combination sort of the strength and the sample size for this analysis. So just like T was a function of correlation and sample size, chi-square is a function of sample size and a function of strength, because how big these numbers are depends on how many people there are. So if you have more people in your table, there's a chance for more of a discrepancy between observed and expected. So chi-square is a combination of signal, how big is the discrepancy, and how many people are you using to index that discrepancy. So this doesn't tell us directly how big the association is. It only tells us how unexpected it is. So in this case, my chi-square would be significant because it's past the 3.84 cutoff for degrees of freedom 1. And it would be written like this, by the way. Degrees of freedom for the chi-square either go in parentheses right next to it, or sometimes it's subscripted underneath. So you'll see either of those written in results. So then we got to do two things. We got to figure out, okay, what is the pattern of the association? What does significant mean? Because reject the null hypothesis is not an interpretation. What is the pattern of how these things relate to each other? That's step one. And then, so how big is it? Because chi-square is a function of both effect size, signal, and sample size. So first things first, what is the direction of the relationship? So I can do this by going across columns or across rows. And so I've written this all down, that way I wouldn't screw up the words. But if I go across the columns, So within the row of non-white, what this is telling us is that there are more non-white people who, more non-white people, yes, who got the death sentence than expected. Or fewer non-white people who did not get the death sentence. You can phrase it either way. And then I can go into the second row and say the opposite. There are fewer white people who got the death sentence than expected. That's the pattern. So more than expected versus less than expected is kind of the analog to a positive correlation versus a negative correlation. And true enough, we can actually convert our chi-square into a correlation and get an effect size that way. So we can also go down the rows. So within a column, we can talk about among the people who got the death sentence, there are more of them who are non-white than expected. Among the people who did not get the death sentence, there are more of them who are white than expected. So that's the pattern that goes with the significant chi-square. So there is an association. The association goes like this. It is significant. And then the last step would be to talk about effect size. Okay, how are we doing? Questions? Okay. So what if I have more than 2 rows? You can do a chi-square, but it gets less useful. So here's another example from the textbook, whether or not someone reports being abused as an adult versus the number of child abuse categories checked. So this is some sort of screener type instrument where more is worse, presumably. And so we can do the same process of, okay, given the number of people who checked no categories, and then given the number of people who reported being abused as an adult or not abused, what are the expected values inside here? And then we can take the difference between each, square it, divide it by expected, and do it across all 8 of these cells. And that number comes out to be like 30. Okay, I don't know what 30 means without a context. The context for what a chi-square of 30 means is its degrees of freedom. So in this case, it's the number of columns minus 1 times the number of rows minus 1 works out to be 3. So degrees of freedom 3 means to figure out all of these 8 cells, I need 3 of them. Just 1 is insufficient, I need 3. And so then, going back, the chi-square I'm referring to is the teal one. So this one that starts down here and loops over, where the critical value is 7.82. So in that context, I know that a chi-square of 30 is more than my critical value, and yeah, the exact p-value is very tiny. So if there was no relationship between being abused as an adult and your history of child abuse, then what you would see are the numbers in the parentheses as your counts. The fact that the actual counts are different than the expected counts is what's triggering this chi-square of 30 to say that these variables are significantly associated. But then how are they associated? In order to answer that question, you would actually have to break this table up into 2 by 2 combinations to talk about what is more expected versus what is relatively less expected. And it is probably better to do that kind of analysis in the context of a model. So this is one of the things that you would learn in my generalized modeling class, which is coming back a year from now, to be able to predict categorical outcomes with either categorical predictors or quantitative predictors. So I would say that chi-squares that work out to be bigger than just a 2 by 2 would be more effectively analyzed in a model. But you'll get a chance to practice a 2 by 2 in your homework. All right. So in terms of other things that I want you to have heard, as highlighted by the fact that we're not using denominator degrees of freedom, so we're not paying attention to how many people we have here in getting the test statistic, that means that just like Z didn't work really well for small samples and we needed T instead, chi-squares not going to work very well for small samples and we needed something else instead. So there are options known as exact tests that are used that work better with smaller samples, and those things rely on simulation, generating expected counts through repeated sampling, and so that's something that you wouldn't necessarily get the exact same answer across programs because of that simulation process. There's also ways of hacking the chi-square to deal with differences in how frequently things are expected. So kappa, for instance, is a chi-square that's used for measuring agreement that corrects for chance levels of agreement based on the frequency with which each category is observed. And there's several other variants of chi-squares that correct for various things like this too. So you may come across these sorts of things in practice. All of them reflect to some extent how far off from expected a given frequency of occurrence is. What you're correcting for in terms of expected varies across these different approaches. And then effect sizes. So, effect size, always important. How big is the relationship in a standardized metric where I can tell you a number and you know immediately what that means? So chi-square, not effective at indexing effect size. Chi-square is a function of how strong the relationship is, how many people went into establishing that relationship's index, and how many degrees of freedom it takes. We can actually, for 2x2 tables, boil that chi-square back down into a Pearson correlation. So it turns out that estimating a Pearson correlation between two binary variables is mathematically equivalent to doing a chi-square test of the two binary variables. Here's the relationship. The only difference in the conclusion that you would draw is whether you're using a chi-square test statistic or whether you're using the t-test statistic that goes with R, because chi-square does not correct for the number of people in your sample, whereas t does. So you will actually see this on the handout that I have that goes with this example, slight difference in the p-value, even though it's the same effect either way, because they're referring to a different distribution. More generally, any parameter that you get a t-test for, you can convert into an R, and here's the formula with which to do so. So you end up with test statistics. You can always strip off the sample size component to it and get your effect size via correlations. So R is a more general way of expressing how related things are that you can use even if those things are not really quantitative. It's just you may have to do so indirectly. For chi-square though, you will see two other kinds of effect sizes that I want, again, put a pin in for your memory, but I'm not necessarily asking you to do in this class. One of them is a risk ratio, and so this is very common in health-related outcomes, particularly epidemiology, public health, and those sorts of fields, where you have huge sample sizes. So this is another table from your textbook. They're looking at the propensity to have a heart attack versus no heart attack for people who are given aspirin versus people who are in some sort of placebo where they take a pill every day, but it's not an aspirin. And aspirin is supposed to help prevent heart attack. That's the purpose of the study. Well, if we look at these cells here, most of the people did not have a heart attack, which is a good thing in terms of, not dying and stuff, but a bad thing in terms of trying to establish the effectiveness of your treatment. So to counteract sort of the vast difference in these sizes of the cells here, you can calculate something known as risk. So for instance, if you took aspirin, your risk for having a heart attack is the number of people in that category divided by the total number of people who took aspirin. Likewise, if you took the placebo, the total number of people who had a heart attack versus over the total number of people who took placebo. And so then we have a risk of 0.9 and a risk of 1.7, and then you can take a ratio of those, and that thing is known as a risk ratio. So if you don't take aspirin, your risk of a heart attack is 1.8 times greater. So that is a way of taking sort of these numbers and putting them into a context that appreciates that small differences can actually matter if there's not that many people who had a heart attack to begin with. So this would be an effect size that goes with a chi-square for situations in which you want to talk about the probability of something happening under this scenario versus the probability of something happening under an alternative scenario. So ratios like these, they're tricky because they basically when something is less likely, it's shoved into the range between 0 and 1. And when something is more likely, it goes from 1 to positive infinity. So I'm not a huge fan of these because numerically I feel like they're easy to misinterpret, but they're very, very common in health settings. And one that's even more common than risk ratio is something called odds ratio. And the big difference between these two is that rather than using the total out here in the margins as the denominator, it uses the number of people that something didn't happen to instead. But it's the same idea. What is your ratio? What are the odds of having a heart attack if you took aspirin? What are the odds of having a heart attack if you took placebo? And then the ratio of the two is your odds ratio. So if something is less likely, it corresponds to an odds between 0 and 1. If something is more likely, it corresponds to an odds between 1 and positive infinity. So I hate them. I'll just put that out there. I hate odds ratios because I can't handle that asymmetry, that all of effect size on the negative side is packed between 0 and 1, but then everything on the positive side goes 1 to positive infinity. I just, like, mathematically, I can't handle that. But these are super duper common and you'll probably see them. So they also get used in regression type models that predict binary and ordinal outcomes. You'll see odds ratios used as effect sizes. So these are alternatives to correlation effect sizes that apply specifically to categorical data. So I wanted you to have seen them at the very least, but I'm not asking you to do much with them. All right. So that gives us to the intermediate summary here. So we have correlations to indicate bivariate associations between quantitative variables. We can do chi-square analysis to get associations between categorical variables, and binary variables are a special case that you can fit into either box. You can estimate a Pearson correlation between them, or you can use a chi-square to get the association. And I wanted you to know how to do this in software. All right, questions before I show you just how easy it is to make SAS and Stata do this for you. Okay. I'll take a quick look and then we'll finish this up next time. I am going to start, this is example 2 again, the general social survey data set. Picked out a few categorical variables for us to play with. Let's see, what page is that going to be? Page 9. So this is example 2, page 9, continuing the story that we left off with last time. So I am going to look at, as an example, the association between two binary variables in this data set, whether or not a respondent is married and whether or not they identified as a man or a woman. Now, no one would likely have a research question involving an association between these two variables. But what I might want to demonstrate is that my sample has been selected in such a way to not confound these two variables, right? I don't want to only have married men and unmarried women in my sample, because then any differences that I'm attributing to gender could also be attributed to marital status. So ideally, I want to show that in the sample, in this context, there is no association between these two things, so that I can look at effects of gender that are independent from effects of marital status. So first in SAS and then in Stata, here's our friend Proc Freak. Things that you would need to change to do this analysis. Number 1, the name of the data set. In SAS, it wants to know what data you want to ask for information from. So rather than example 2, for instance, this would be homework 2. Table is where you tell it what the names of the columns are for which you want a cross tabulation. So notice this thing right here, that asterisk. That is how you tell SAS that you want all possible combinations. So if I were to forget this asterisk and do this right here, I would get a count of frequencies and percentages for gender, and I'd get a separate one for marital status. I wouldn't get the cross tabulation. So the star is necessary to get them in combination with each other. I am suppressing additional output that's going to not be necessary in terms of the number of people in the row or the column, and I have the percentages. Here are the keywords that I need to generate expected frequencies, as well as to get the chi-square analysis, and I'm doing an alpha of 0.05 as usual. And here is my output. So the first row in each of these little cells is the count of people who are in that combination of categories. So in this sample, I had 197 men who reported not being married. I had 166 men who reported being married, and that means the total number of men was 363. Likewise, 200 women, 171, and the total's down here. The second row is expected frequency. So by the way, this information that Proc Lisa has written out for you on the right here is available right here. That's where that came from. So frequency, then expected, then percent. So the second entry in each of these cells is the expected frequency. If these two variables had nothing to do with each other, how many people would I expect in that combination just based on the margins alone? So based on how many men are in the sample and how many not married people are in the sample, what would I expect for the combination of the two? And it's 196 men is expected. 197 is what I got. Likewise, 166.6 expected, 166 is what I got. So just eyeballing these things, would you say that it looks like there is a relationship between these variables, thumbs up, or there is not a relationship between these variables, thumbs down? We had a couple votes for there is a relationship. And then we got some thumbs down as well. Yeah, you can foreshadow the results, by the way, with the next table. There may be a relationship, but it's pretty small. There's always a relationship. It depends on how many people you have to say whether it's detectable or not. But yeah, 197 versus 196 is pretty close. Similarly, 166 versus 167 is pretty close. And if I do the chi-square that adds up the difference between observed and expected, square that, divide by expected, and do that across all four cells, I get a chi-square test of this right here. So 0 to 3 decimal places. That, coupled with the corresponding exact p-value, is telling me that the chi-square is non-significant, meaning there is no relationship between these two variables because what I observed is pretty much what I expected. The difference between observed and expected is not big enough to say that that is into unexpected territory. So I would see discrepancies between what I found and what I expected this large, like 92% of the time, if there was no relationship. Okay, with me so far? So I'm retaining the null, saying that there is no relationship. Down here, by the way, that thing right there, we mentioned this last time in class, the phi coefficient. Do you remember what that thing is? Or does anybody remember from earlier in their lives? If you don't, that's okay. You can just say nope. Nope. So a phi correlation is a special name for a Pearson correlation between two binary variables. There's a computational shortcut to computing the correlation that you can take if the variables are binary, and that's what it refers to. But for all intents and purposes, that's the Pearson correlation that goes with that chi-square. It gives it to you. So this is a way of more directly indicating what the size of the association is between these two variables and the direction. Cough, cough, homework question. So the size. This is a correlation that is pretty much zero. So there really is not a relationship between these variables, but it is slightly positive. So what does a positive correlation mean between two binary variables? That one can be tricky because the interpretation depends entirely on how those binary variables are coded. So normally if I had numbers here, if I had quantitative variables and I had a positive correlation, what would that tell me? Yeah, I'll take gestures.
Is it that X and Y are going up or down in the same direction?
Yeah, as X goes up, Y goes up, or as X goes down, Y goes down. That's what a positive correlation means, is that there's a positive correspondence in the same direction. So if I try to map this onto this table, as X goes up, well, I have a variable where men are 1 and women are 2. So as X goes up means if you go from being a man to a woman, like in women, is sort of the as X goes up. And then likewise, unmarried is a 1 and married is a 2. So as X goes up, Y goes up means women are slightly more likely to be married. Do you want me to say that again? Logic, it's a twist in your head. But in binary variables, you can still use the same logic as a positive correlation means as X goes up, Y goes up. But what up is depends on which group has the higher coded value. And that is completely arbitrary. So you have to look at your value labels. For instance, up means if you're a woman instead of a man, and up because 2 means that you're married instead of unmarried. So a positive correlation that is created by this table is that women are more likely to be married than not married, because that's what it means to go up in Y, to be married rather than not married. Okay, Jerome, question?
So in a sense, this is kind of like when we have Spearmans where the two numbers are related to the second variable that we're talking about. Or not necessarily, but like, I guess they're attached to a label and not necessarily, I don't know how to ask it, but basically men would be 1 and women would be 2. And then those are increasing as married is 2 and unmarried is 1.
Everything you said is right, although in this case, Spearman and Pearson would give you the exact same information because this variable is already like a rank order because there's only 2 categories. If we had more than 2 categories and it was ordinal, then potentially you would have a different relationship if Spearman had smushed it in, so to speak, if any of the categories had gotten omitted in terms of the middle. So I actually helped a student from this class get through a research paper where they were reporting correlations between grouping variables and various outcomes. And it turns out that the person who wrote the paper misinterpreted one of their correlations. So there was a variable in the analysis that was a treatment group versus a control group. And one of the outcomes was Therapeutic Alliance, which, any of you counseling people, can you tell me exactly what that is? Oh, Emily, would you like to tell us?
Yeah, Therapeutic Alliance would be like the relationship between the client and the therapist and how effective it is on accomplishing therapy goals.
Okay, so more is better, presumably, to be more
Yes.
aligned or allianced, whichever you want to say. Yeah. So if your treatment was effective, what kind of correlation would you expect to see between treatment group and Therapeutic Alliance? Positive or negative?
Positive.
Positive if treatment was coded 1 and control was coded 0, right? Because that means as you go from control to treatment, your alliance goes up. But if you coded it the other way, you would expect a negative correlation. So it depends entirely on the coding scheme how to interpret the direction. And this doesn't work if you have more than 2 categories, because then you have more possibilities for what up is relative to some sort of baseline.
Lisa, can I ask a quick question about this example?
Yeah, let's keep it on this page then.
The women is higher because it's coded 2, not because it's a higher number.
Those are the same to me.
Okay, so sorry. So like 200 instead of 197, or like technically it's 371 versus 363 in terms of there's more women.
Oh, okay. I see what you're asking. No, it is entirely because 1 is man and 2 is woman.
Okay. Just want to make
Yeah, so you may have decided who gets to be the 1 versus the 2 based on the frequency. But yeah, and so this is another instance where, like, the fact that I put a label on these variables. So in the data set, they were stored in 1 and 2. And the fact that it's printing man and woman is because earlier in the code, I attached a labeling convention to that column. That way, when I got the output, I didn't have to do the mental arithmetic of like, okay, who's the woman and who's the man? What does 2 mean again? But had I written the labels without the numbers attached, then potentially I could have ended up with a confusing set of results. So like if I had male, female is alphabetically before men, which would have flipped the order of the variable.
Okay.
So great question to make sure that you understand like why it is higher. It is entirely higher because of my a priori decision that 2 is what women means.
Okay. Just want to make sure I understood. Thank you.
Yeah. At least that's the way that it works in SAS and Stata. If you let the other programs do the dummy coding for you, they might use rules based on sample size potentially, although I haven't seen that. It seems like something could be done. So in homework 2, for instance, you're going to get a chance to interpret a 2-way table, get a chi-square for its significance of its association, and then try to put words on it. What does the association actually mean? What is more expected than what? And that relates to the idea of a negative correlation versus a positive correlation. And so in this case, it's sufficient really just to look at this cell right here and say that married women were more expected than married women were observed with a higher frequency than expected. 171 is higher than 170, so married women were more frequent than expected. If the pattern was backwards, if there were fewer married women than expected, that's a negative correlation. So recapping, the significance test comes from chi-square. Chi-square is an index of both the size of the association and the number of people going into it. The p-value that shows up corresponds to that chi-square. But to be able to talk about the chi-square's association, stripping off the number of people and just drilling down into an effect size, one way to do that is to interpret the phi correlation, which is your Pearson correlation. And then odds ratios and risk ratios are other ways of doing that you can ask for from the software, but which I did not include here. And here is the correlation down below, just to make the point that I'm not crazy. These numbers match, but the p-value is slightly different. So the p-value from the chi-square is 9217. The p-value from the correlation is 9218. And that is because the correlation is using t to get the p-value, whereas the chi-square is using chi-square. T pays attention to the number of people, chi-square does not. So they're different in the same way that T and Z is different. All right, questions? Then it is 1:45, time to sign off. Let me know if you need any help with homework 1. Office hours start at 3:15. Otherwise, I hope to see you all on Thursday. So, see you then. Have a good one.